Recording started. Sharing the screen. All right. So last lecture. Oh, sorry. Last lecture we stopped here. So we already mentioned in the previous lecture about the difference of real and reactive power and apparent power as well. Then here, like some factors that's impacting the real power and reactive power. So the overall thing, which is related to the synchronous generator. So the traditional generator for the power supply, traditional generator is a three-phase synchronous. And the synchronous speed, as we know from machines class, Ns equals 120 times F divided by the number of poles. The number of poles used to be fixed. However, the only impacting factor is the frequency. We can realize that the synchronous speed is directly proportional to the frequency. So if the frequency goes high, the speed goes high. If the frequency is low, the speed goes low. The vast majority, or like most likely, our target is to make the frequency, for example, 50 hertz. Then assume the number of poles is 4, so it will be 120 times 50 divided by 4. This yields to be, I believe, 20 divided by 30, 30 times 50. I think 1,500 RPM. This is the speed in RPM. Here's an example. Assume number of poles is 4 and the frequency is 50, then this yields to 50 RPM. However, if you want to make the frequency 60 hertz, then it will be 120 times 60 divided by 4. Then this yields 60 times 30. 6 times 3 will be 80, so 1800 RPM. So we realize that at 60 hertz frequency, the speed is faster, while at 50 hertz, the speed is low. Now, the other thing that I want to mention, let's assume this scenario. Assume the power generation for a certain generator equals to be 2,000 megawatts. And of course, to get the load balance, so assume the load power balance, which is the load is, I would say 1950 megawatts, and the loss is 50 megawatts. To maintain the power balance, sum of generation equals sum of load plus sum of losses. So the sum of generation 2000 equals sum of load 1950 plus 50, which is 2000, then that's fine, that's correct, which is satisfied. Now, in this scenario, let's assume there is a fault going on and the load has been decreased significantly to be P load 2 to be, I would say, 1800 megawatts. The losses remains the same, 15 megawatts. So when you do the sum, 18 plus 50, which will be 1850 megawatts. This is load. While the generation, 2000 megawatts. So there is a mismatch. We call it power mismatch. Which means there is extra generation. Extra generation. That extra generation by 150 megawatts. Now my question is, where does the extra generation, where will it go? I mean, it will not go to as losses. There is an 150 megawatt extra generation. Where's it supposed to go? What do you think?
typically, if it have storage systems, they would go, if you have a storage system, they would go to a storage system, or maybe a flywheel if you want to conserve it for later.
Let's assume there is no, there is no we cannot save, there's no storage, I would say. Assume there's no storage. Where will 150 go? There is no storage, there is no, recycle for the energy. I would say there's something we call AGC, automatic generation control. So the automatic generation control will will make the generation to reduce the generation. So the generation will be reduced to be 108.50 to match the demand. But it will take some time. It will take maybe I would say few seconds or maybe several minutes. So it will take there some period. The generators, the generation 2000, now they will be ramped down to be 150. Okay, so before, after the problem solved, there is no extra generation. But how about what's happening here during the transients? During the transients, what's happening? It's going down. By going down, this means during this transient period, there's an extra generation that we cannot handle. So how will it go? As you said, like the energy is conservative. Then the thing about it, let's imagine some scenario. Then let me go back to it. Imagine the following scenario. You are in a shopping mall or whatever in the hypermarkets, and you are pushing a shopping cart. So you are pushing a shopping cart. There are some stuff on it. Then here is like you are pushing the cart. Then when you are pushing the cart, as we know, the torque speed characteristics. So the torque is directly proportional to the speed, right? So if you're pushing this with a constant torque, it will give a constant speed. Once you increase the torque, the speed will be increased, correct? I think we all agree on that. Now, the thing about it, assume you are pushing for the same torque. Assume torque is constant, same torque. And for instance, one of the items was falling down. What will happen to the cart? Are you gonna, if you are pushing with the same torque, what's happening? What do you think? Are you gonna, the speed will be increased, will be fixed, or will be decreased? What do you think?
The speed would increase, right? Since we have less weight now.
Of course, that's right. So the speed will be increased. Why the speed is increased? Because you are pushing with the same torque, then less weight goes out, or one weight goes out. Then for the same torque, it will be you will push for the speed will be accelerated, or the cart will be accelerated. So how to maintain to go back to your original speed? You will reduce the torque. Is this correct? If you to return to go back to the same speed that was done before, you will reduce the torque. And this is what's happening for the generators. When you have extra generation, the generator will accelerate. So the speed of the generation will be increased. What you're going to do to maintain, to go back to the original speed, the amount of generation will be reduced, or the torque will be reduced. So this, as a result, we will go back to the original speed by reducing the torque, or reducing the load, or reducing the power generation. So the same thing happening here again. If there is extra generation, the generation or the generators will accelerate. If there is, how about the opposites? If there is extra load but not enough generation, what will happen to the generators? They will deaccelerate. The speed will be reduced. Why? You can go back to the same scenario. You are pushing the shopping cart, and somebody put some items on it. If you are keep pushing with the same torque, your speed will be reduced. Then the same thing for the generation, which is basically once or this extra generation will go as the something we call it the transients. Extra generation will make acceleration of the generator. Okay? So now I assume you got it. Now, how can we translate this into electrical thing? I mean, extra in the mechanical thing, we will see the acceleration is will be accelerated, which means the rotational or the synchronous speed will be increased. What will happen to the frequency? Let's go back. Where is it? I mentioned it. I think it's already been mentioned here. We know the speed and the frequency are directly proportional. So if the speed goes up, what will happen to the frequency? It will go up. So as a result, we can say when you have extra generation, the frequency will be larger than 50 hertz. If we have extra load or less generation, the frequency will be less than 50 hertz. But keep in mind, the frequency must be bounded between 49.5 hertz up to 50 hertz. This is the worst case. If the frequency is below than 49.5 hertz, the generator will trip, will be out of service. If the generation more than 50.5, then the generation also will trip, it will go out of service. So I would say again, extra generation, which make the accelerated, the synchronous speed will be accelerated, the frequency is high. If, here's again extra generation. If there is extra load or less generation, what will happen to the speed will be reduced. As a result, the frequency will be reduced. Okay, does this make sense? Any question?
So basically, we only we have like variable frequency depending on if it's extra or less, extra load or extra generation.
Yeah, I mean the main target for the synchronous generator is to maintain a constant frequency operation. Our target is to make it exactly 50, but sometimes some load fluctuation can happen. This load fluctuation will cause speed fluctuation and will cause frequency fluctuation. The generator prefers to work on a constant speed, constant frequency, but in real life, it is not 100%, constant. It can variable depending on the load, but with very slight differences. Again, it can be between 49.5 up to 50.5. That's the maximum allowable change, no more than that. And this is the worst case. I would say like 0.5 hertz difference. This is too much. But basically, I mean, if you go, when you go to the control room, you will see, I mean, very slight changes, like maybe in maybe 0.1 or 0.01, something like that. At 0.1 at, I mean, you will see it at max 0.1. But I would say like in case of contingency analysis or emergencies, there is 0.5 hertz can be allowed. Okay. Now, as I said, the real power is associated with the frequency. You have extra generation, frequency up. Less generation, frequency down. This for the real power. However, the reactive power is associated with the voltage. So if you have extra reactive power, the voltage will be high. If you have low reactive power, the voltage will be low. Okay? That's the thing that you need to keep in mind. Let's look at the factors impacting the real power. The real power, to make the frequency up, you need to have extra generation. You can look at here the like the arrows that make boosting. Assume this is the frequency level, like this 50 hertz, and we need to boost the generations or the real power. How can we boost it? Using the base generator, the adjustable generator, renewable energy sources, and reserves. Reserves like spinning reserves, energy storage systems, etc. How to boost The real power. I'm sorry. Okay. However, the things that's lowering the frequency or adding the loads, which is basically the base loads, adjustable loads, variable loads, the power losses, all of them are a factor, which is basically the loads, including the losses, will make the real power goes down. The other thing, the reactive power. The reactive power, which make the reactive power goes down, which is the load behavior. Our load behavior is basically resistor and inductor. Why is it resistor and inductor? The vast majority of the loads are based on industrial loads. The industrial loads that consuming a lot of energy, this is based on motors. When there is a motor, as we know, the equivalent circuit of the motor is based on inductor. That inductor will absorb reactive power. While also in addition to this, the residential at home, at our home or apartments, whatever, we have the which is called the different motors. So we have the washer, air dryer, the refrigerators. All of them are based on motors. The air condition as well, based on motor. So all of them based on motors, induction motors. There's the behavior of the induction motors is to have an inductor. That inductor will make consume reactive power. So the vast majority of the loads, or our loads, are RL load that consuming reactive power, which make it push it down, push the reactive power down, or in other words, push the voltage down or reduce the voltage. Then in order to maintain this, we have several, to maintain the voltage to go back to the original value, we have several options. One of the options, tap changer. The other option is to use the capacitor or capacitor bank, or the other thing, which is using the power generated from the synchronous generator. Okay, so why we are using the capacitor? As I said, the vast majority of our loads is inductor. As we know, the impedance of the inductor is J omega L, or in other words, which is called JXL, which is positive. However, the capacitor, it used to be 1 over J omega C, 1 over J, which is negative J, so negative J divided by omega C, or in other words, it's negative J times XC. Then when you compare ZL and ZC, you will realize this is positive and the other one negative. Then we can say the capacitor is the opposite of the inductor. So the capacitor is the opposite of the inductor. Therefore, since we have the vast majority of our loads are based on RL loads, therefore we need to install capacitor banks or switched capacitors to the power system to compensate and reduce the inductance impact. How can we reduce it? By adding a capacitor. Why it is switched? Why it's not connected forever? Because it depending on the load behavior. Sometimes maybe you can have a light load, then there is no need to turn them on. Low reactive power consumption, so there is no need to add extra reactive power. If we keep it, or if we keep it forever, it will make an over voltage because the voltage will be very high while there is low inductive load, then it will make a bad impact. Our target is to make it in the middle, which is not to increase to the voltage too much and not to decrease the voltage too much, which is keep it in a safe range. How can we increase it? By adding a capacitor bank. How can we decrease it? Turn off the capacitor bank. That's the thing. That's how we do. While the load behavior, we don't have a control on the load behavior. It depends on just like the time of the day. Then that's how it's happening. The other thing, have you ever heard of Ferranti effects? Does anybody have Ferranti? Yes.
Frontier effect?
Yes, Ferranti in power system. I'm not sure about the spelling. I think it's FRRENTI effects. Okay, anyway, I think maybe you should take it in power system class, but let me tell you a little bit. So as we know, the equivalent circuit of the transmission line is based on inductor and resistor, right? This is for short transmission line. However, for medium transmission line and long transmission line, there's a pi model by adding a capacitor. This is C over 2, this is C over 2, this is L, this is R, okay? Now, the thing about it in Ferranti effects, as we know in the ABCD matrix, V sending, or I mean, it's V receiving. Uh-oh, sorry. V receiving, I receiving equals to be A, B, C, D times V sending, I sending. I think you are all aware of this. Now let's look at the V receiving. V receiving equals A times V sending plus B times I sending. Okay, sometimes under light load, whereas RL is very low, the capacitance C over 2 of the transmission line, this is C over 2, both of them, they will provide reactive power larger than the reactive power of the load. Okay, so what's the point? This leads to be extra reactive power, even though it's not in purpose. We don't have a control in the reactive power supplied by the transmission line, by the capacitance. This extra reactive power cause what? Cause extra high over voltage, or cause the voltage to be high. Voltage at receiver will be high. Okay, what's then the result? This yields to be, let me see if you have enough space here. This yields V sending, V receiving larger than V sending. So assume at the substation, you are providing, for example, 400 kilovolts. Then at the end will be 420 kilovolts at the receiver. That's kind of weird, but this can happen, especially in extra high voltage, and can happen under light load. However, under heavy load, what's happening, which is basically the sending is 400 kilovolts, the receiver is 380 kilovolts. So the sending larger than the receiving. This one is very low, then we need to increase it. This is in heavy load. While in light load, this is very high, we need to decrease it. How to increase the voltage? By what? Turning on capacitors. Turn on capacitor bank. While if the receiving larger than the sending, again, which we used to call it weird, and again, this is called Ferranti effects. Ferranti effects, which means the receiver larger than the sending, and that's something, I mean, not common, not usually common, but we used to see it in extra high voltage, then we need to decrease it. So again, to increase the voltage at capacitor bank, to decrease the voltage, what should I do? Turn off capacitor bank. Turn off capacitor bank. But there are some scenarios that all of the capacitor bank are turned off, but there's still this receiving voltage larger than the sending. So what should I do to decrease the voltage if all of them are turned off? The thing, it is larger because we have a capacitor. How to cancel the capacitor effects? By adding inductor. So sometimes turn on inductor bank. But we don't used to call it inductor bank. In electrical engineering in the power substation, we used to call them reactors, not inductor bank. So we have reactors in Jordan in several substations, especially in 400 kilovolt and extra high voltage. Again, the main reason for that, because of the Ferranti effect. Ferranti effect can happen on long and medium transmission line, not on short transmission line, and it can happen only during the light load. When is during the light load? It can be, for example, during the weekends, like in Friday, or like during Saturday, or during the night. We can see the Ferranti effect significantly large. What should I do to decrease the receiver voltage? Because, I mean, if it is very large, it will impact the customers and impact the other substation equipments. So we need to decrease it. How can I decrease it? By turning on reactors. The reactors will absorb reactive power and turn off all of the capacitors until reaching the desired level. Okay, does this make sense?
Yeah, makes sense.
That's great. Now, the next thing is here how to, imagine the electrical supply based on the real power. Assume there is a water tank and the depth is the frequency. So here is, for example, the depth is 60 hertz, or you can assume it like, for example, 60 centimeters. Then the depth is 60 centimeters. The electricity supply is these water faucets. And the other thing, which is those are the customers, that the water goes to the agriculture, the industrial, commercial, residential. Then our target to maintain a constant depth is to make sure the water flow here equals the water flow here. Then we will make sure to maintain the water depth. If there is extra load, what will happen to the depth for a constant electrical water supply? It will go down, it will be reduced. The depth will be reduced if there is extra load. If there is extra generation, if there is extra generation, what's happening? With light load, then the frequency will be high, or the water depth will be high. The water level will be high. Okay? Our target is to make sure that the water level is constant at 60, for example, centimeters. That's our target, to make sure it is within this. This is how you can simply imagine the real power generation and the other thing. Okay, now the next thing, some overview from power system class, the power flow. Now we have bus I and bus J. What does bus mean? Bus means substation, which is substation I, substation J. You can, for example, assume substation I is Madaba. Substation J is, for example, Queen Alia Airport. Queen Alia Airport. So this is substation. Then we have, the transmission line. This is the transmission line for, which is the big towers that's connecting the high voltage tower, 132 kilovolts. This is the transmission line. If the distance is short, then it will be R plus JX, which is RL. If the distance is large, which is medium, we have short transmission line, then we have resistor and inductor. Medium and long transmission line, resistor, inductor, and there is a capacitor here and capacitor here. This is called the pi model. There is another model which is called T model, like this: RL, capacitor, and RL. So the thing here, we used to say this is R, this is L, this is R, this is L, this is C over 2, C over 2. Or you can use, T model is applicable in both. You can use either T model or pi model. In this one, this is R over 2, L over 2, R over 2, L over 2, and this is C. Okay? That's the thing. But assuming a short transmission line, there is no capacitance effect, then we have R plus JX. Okay, this is for bus. If you need to calculate the power flow between substation I and J, or between Madaba and Queen Alia Airport, it will be like the real power plus the reactive power, which is V times I conjugate. The I conjugate, just recall, assume I equals 30, oh, come on, where is it? 30 angle 90 degrees ampere. Then I conjugate means just reverse the sign of the angle. So it will be 30 angle negative 90 degrees ampere. So the conjugate reverse the sign. Here it used to be positive, while here with the conjugate it becomes negative, and the vice versa. Now, how about to calculate I? I, which is V, the voltage difference divided by impedance. I here will be delta V divided by Z. So delta V divided by Z, which is VI minus VJ divided by R plus JXL. Then for simplification, to calculate the real and reactive power, substituting VI and the current, keep in mind all of it is conjugate, then you put all of the conjugates here. Then the next thing is to keep in mind VI times VI conjugates. This means VI as a magnitude square, while VI times VJ conjugates, this is VI times VJ times theta I minus theta J. Why the next one there is no angle, the first one there is no angle? Because it is theta I minus theta I, which is equal to 0. Therefore, it has been eliminated, so it will be a real number. Then that's what we have here, V squared, here VI, VJ angle, theta minus theta, theta I minus theta J. Come on, sorry. Then we assumed the angle difference gamma, which is theta I minus theta J. Then after simplification, converting polar coordinates to rectangular coordinates, this is the real power, and this one, the other one is reactive power. Now this single line diagram, as we know from power system class, we can convert any single line diagram. For example, assume this is a voltage source that associated with the grid impedance, or even though there is no need to put the grid impedance. So it is a voltage source, then there is a bus bar, then there is a which is called the transformer, then there is a big transmission line, then another transformer, then connect this to the another generation units and to the load. This is the single line diagram, and as we have learned from power system class, we can convert this one to be, this is the generator, this is the transformer, then the transmission line using the pi model is this one, then the load is, which is this one, this transformer is this one as well, then the last one, this generator is this one. I think you're already familiar with this from power system class. But keep in mind, this is a three-phase system. So this is phase A, this is phase B, and this is phase C. Assume the system is balanced, then there is no need to draw all of the three phases. You can do something, we call it per phase equivalent circuits. Per phase equivalent circuit by taking and listing phase A as a reference. So when you list phase A as a reference, it's enough to solve the circuit for phase A, then to find for the rest of the phases will be the same because they are balanced. Then you can say calculate for phase A, then multiply by 3 to find it for the remaining phases. Here is like taking phase A as a reference. This is how it looks like. Again, this is the generator, this is the transformer, transmission line, another transformer, load, and generator 2. Then here is the which is called the single line diagram for that, which is the same thing that I used to draw. The other thing that when you look at it, there are some symbols that you need to be familiar. Like, for example, what does this mean? What does this mean? What does this, etc. And what does this mean? What does this? So the symbol that you need to make sure that everybody must be familiar with this. When you see a circle, this means this is a rotating machine. It can be either generator or motor. So there must be a word G for generator and the word M for the motor. The other one, bus. Bus, which is the bus bar, which is, I would say, like this is the substation. This is the substation, which is the bus bar. Then two winding transformer, the transformer that has one input, one output. So one, two windings. Three windings transformer that has multi inputs, multi outputs. So one, two, three. Therefore, this is called three winding transformer because we have three, and the other one was two winding. Then the other one, when you see the square, this means a circuit breaker. And the circuit breaker, it can be either the SF6 circuit breaker or the oil circuit breaker, or it can be the vacuum tube circuit breaker. We will talk, by the way, about them later. But that's what we have in here. Then the other thing, air circuit breaker, the circuit breaker that there is no insulation material around it, so which is basically on the fresh air. The other one, disconnectors, or we used to call them isolators, and we already discussed this before. So the isolators will provide, a clear vision that their power has been out, is out. Then the last one, which is the fuse that used to protect many equipments, like for example the transformers and the other thing. And the fuse will basically detect if there is a high current, then it will. If there is a high current, it will be melted. Then you need to replace the fuse by another one, or first solve the issue, realize where's the problem, then replace the fuse by another one, then return the power back. The other thing, delta, this is the delta connection for the, symbol delta for the three wire system as we know. And there is a Y alone without, a wire. This makes it Y ungrounded. Then there is another one Y grounded, like what we see here, grounded and ungrounded. Come on. Then the other thing, there's the transmission line. Then there is a load, static load. Then there is a few disconnected. Then there's a lightning arrestor to protect from lightning strikes. Then there's a capacitor bank to be turned on to increase the voltage whenever needed and to improve the power factor. Then there are two things remaining, which is CT and VT. CT, which is current transformer, VT, a voltage transformer. Both of them are being used only for measurements. They will not provide power to the system. They are only used for measurements, for measurement purposes. So you will find them at the beginning of each substation to measure the current and measure the voltage. Then it will go to the SCADA system. Then it will go to the control room. Then they can know the voltage and the current. If there is extra voltage or there is, high voltage, then the overvoltage protection will work. If there is a high current, then the overcurrent protection will work to protect these equipments. Per unit system. I think we already,
Doctor,
you already
I have a
familiar.
question. I have a
Yes,
question.
sure.
Yeah, in the previous slide.
Yes.
Yeah, the next one. The previous one.
Yeah. Here?
Yeah, where do we use the three winding transformer in distribution?
Yes, we can use it in distribution. Let me show you an example. In Jordan, the distribution transformer basically will convert the three-phase transformer from 33 kilovolts to be 0.4 kilovolts, but three phase, it's not a single phase, which is basically transformer, 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 like this. Okay, 33 kilovolt, or sometimes we go 11 kilovolts. That's in Jordan. However, in the United States, the situation is different. They will take a single phase 7.2 kilovolts. Let me fix it. 7.2 kilovolts. Then they are using three winding transformer. So the voltage from here to here, 120. The voltage from here to here, 120. And again, from here to here, 7.2 kilovolts. Then three lines will go inside the home. Then you will see three voltages. So here is phase A, this is a neutral, phase B, and here 240 volts. Then in the breaker panel, you will see, here is the breaker panel. You will see this is for phase A. You will see this is bar for phase B, and this is for the neutral. Then you will see some applicants connected, like some loads connected here. This is 120 volts. Some loads connected here. This is 120 volts. Some other loads connected between here to here. This is 240 volts. That's why in the United States, in residential, I would say like residential, in the residential, we have 120 volts plugs and there's 240 volts plugs. Which one is more common? Of course, the 120. How about 240? 240 is used for high energy applicants. And as an example for high energy, which is basically air condition, a dryer, water heater. Some of them, water heaters, it depends on the capacity. But that's, I mean, some applicants, that's 240 is being used, while the rest, or the vast majority, based on 120 volts. Why we are using 240, not 120, on the air condition or dryer or water heater? Because they are consuming a high amount of energy, making the 120 volts insufficient of supplying enough power. Therefore, to get this, I mean, a good amount of power by not increasing the current too much, we need to increase the voltage to be 240. And that's the drawback of the 60 hertz and the, I would say 120 volt system, which is basically we have dual voltage. We have 120 and we have 240. It depends on the applicants. However, in Jordan, it's 230 volts, and there is no need to do any of those. There is no need to make it larger. I would say in Jordan or even in the United States, if the load is too much, I mean, is very big load, then we will replace it by a three-phase. So replacing the not connecting single phase to the home, connecting three-phase to the home. And I think this can happen in many commercial and some residential areas. So I would say in Jordan, we will use only single phase. If there is more energy, we will use three-phase. However, in the United States, it is based on single phase. Here's 230. This is the three-phase will be 400 volts. In the single phase, it used to be 120. Then if we need more energy, we will use, which we call it the biphase, or which is called this, the three-winding transformer. Then it will give you 240 volts. Then if you need more, we will switch to the three-phase, which can provide, I believe, 208 volts. I think it's more than 208. I'm not sure. But we'll switch to the three-phase. Okay? Any question? So here's like an application windings. Yes. Sorry. This is a three-winding transformer. All right. Now the per unit system, we already familiar with the per units, which is the physical quantity divided by the base value. Go for the quantity. I'm gonna go fast because we're already aware of this and we already know this. So we have learned this from the power system class, but we will just go an overview to make sure everybody's familiar, to make sure everybody to remember and recall the per units and quantities. So here is IB equal S divided by V, which is in order to time the base, I base equal S base divided by V base. S base used to be given as volt ampere in base, and when we have the V base, which is the voltage that we need to calculate, or the per units, the Z base equals V base divided by I base. Keep in mind that to be familiar with these equations. Then the thing here that maybe that you need to think about it, the per unit nu is different than the per unit given because it depends on the different level or different, which is called the references. So we can say Z per unit nu equals Z per unit given times megavolt ampere nu divided by megavolt ampere given times kilovolts given over kilowatt nu squared. So we can notice that they are the opposite of each other. So nu here in the denominator, the other one in the numerator, and the vice versa here. And don't forget the square, of course. Then this is how to calculate this. So you need to be familiar with this equation. Yeah, by the way, I forget to mention in the exam, you are allowed to have a notes sheet handwritten, single side, handwritten, and the size of the sheet is A4. Only equations. So if you after to forget some equation, you can write it in your sheet. Don't forget in that sheet to write your name and ID. That's by the way, this is allowed for the first exam, single sheet, one side single sheet. In the second exam, one side single sheet. In the final exam, double side for a single sheet, and must be handwritten. I mean, nothing printed is allowed. Don't write any example. It must be equations. Don't write anything else. Just equation that you need. Okay, then here is how we calculate the voltage Z per unit. Let's look at this example. So for the currents, we need to calculate the load currents and the load voltage in this example. The problem of this one, we have two transformers. These transformers can make a big, can be a big burden on us. Keep in mind the voltage here is 8 kilovolts. The voltage here is 80 kilovolts. Then the voltage here is 16 kilovolts. Then we need to do the calculation. When we convert everything to per units, the problem will be easier. So the first thing, start with this source. This is 8 kilovolts divided by 8, which will be 1 per units. So this source will be 1 per units. The other one, let's calculate the impedances. So in order to calculate the impedances, sorry, again, this is 1 per unit, correct? To calculate the impedances, we need to calculate the Z base. We need to calculate the Z base here. Which is, we call it Z lifts. Z base lift. Then we calculate here Z base middle. Then the last one, Z base right. So how to calculate Z base, which is, as we know, that S equals to be V squared divided by Z. Therefore, Z as a magnitude will be V squared divided by S. Okay? Then we apply it for each left, middle, right. We get each one the base value of first one. Come on. The base value of the first one, the base value of the second one, and the base of the third one. Once you calculate the base, you can calculate the per unit for each one. So the first one will be divided by the base of the left. The second one will be divided by the base of the middle. The third one will be divided by the base of the right. So and that's what we did here. Then we calculate everything in per units. Now, when you look at this one, this is the circuit in per units. No longer transformers are here. Then you can calculate the currents and the voltage easily. How to calculate it? It's a single loop. Then you can say I will be V load divided by the sum, not V load, V source by the sum divided by the sum of the impedances. So which will be 1 angle 0 divided by J1.56 plus J 0.375 plus J 0.39. Then that's how we calculate the currents. And that's what we did here, which is 0.22, angle negative 30.8. But keep in mind, this is in per units, not in amps. How to calculate it in amps? You need to calculate I base first. Then after that, you can multiply to find it in to find it in amps. That's same thing for the voltage. The voltage will be V load equals I times Z. So I times R, which is 3.91 times I. Then 3.91 times I, which will be 0.859, angle negative 30.8 degrees per unit. Then in order to calculate the power, the total power for the load will be V times I, which will be V load squared divided by Z. Then we calculate it as 0.189. Then in order to calculate the current, we need to calculate the current base first. To calculate the current base, we calculated it here as 1250 amps. Then multiply the currents that we got by the base 1250, then it will be 275 angle negative 30.8 degrees. This is the current in the middle section. Now the polyphase. So what does polyphase mean? Multiple phases. Okay, what's the point? As we know, the power system have three phase. It's based on a three phase. Now my question or my concern, why it's three phase? Why not two phases? Why not five phases? Why not seven? Why did they choose three phase system? Okay, before answering this question, let's look at this circuit. So here in this circuit, assume you need to supply 1 megawatts from substation 1 as a single phase to the load, and assume this costs 1 million. So we have two wires that supply 1 megavolt and supply 1 megawatt, sorry. Then that's two wires supplying 1 megawatt here from the source to the load. And the number of wires, we have two wires, as I said, to calculate 1 megawatts. Assume we need to use 2 megawatts, or the load has been changed to be 2 megawatts. The current system capacity cannot handle more than 1 megawatts. So what should I do? One of the options is to replace the existing power line by another power line that can handle more currents, but this one is costly. And the other scenario to make sure maintain the system or to provide 2 megawatts by basically installing another circuits like this. So here we have 2 times the power. In this scenario, will give you 2 times the cost, right? The cost has been doubled. Is there any scenario that make it cheaper? The answer is yes. By making biphase. Biphase, which is basically we have 3 wires, phase A, B, and neutral. Then in this phase, we do have the we are using only 3 wires. So 2 times the power, here 2 times the cost, which is 4 wires. But in this one, 2 times the power will give you 2 wires, 3 wires. In terms of the cost, it will be 1.5 times the cost, 1.5 times the cost, which is basically saving more money. So as a result, choosing 3 wires cheaper than you choosing 4 wires, especially if you are connecting the power line for very long distance, then you are saving a lot of money. So that's a good thing. We're using biphase. However, there's another approach that's way better than this. By using the 3-phase, 3-phase, 4 wires, 3 times the power, which is 2 times the cost, because we are using 4 wires. then that's great. That's a great approach. Now, the other thing, which is, can we make 5 phases, 5 times the power, which will make it 6, which is 3 times the cost? Is this one cheaper? Yes, this one's cheaper. Why we are not using 5 phases? Why not 7? Why not 10 phases? What do you think? Why we are not using it? The thing, even though theoretically 5 phases is better than the 3 phases in terms of the cost and cheaper, but applicably, I mean, when you increase the number of phases, like 5 phases or 7 phases, you need to have a very big tower that can handle the conductors. For example, like this tower. So for example, here is one conductor, 3 phases. If you need to 6 phases, then we have 1, 2, 3, which make it the power, the tower of the high voltage tower, very large in size, and which will make the, I mean, infrastructure very high. When you which make it the overall land, you need to have extra land, and the other thing, which is the basement of the towers, will take a lot of concrete, and we need to have a lot of steel that can handle for to establish the towers that can handle very large value number of phases. So economically, we realize that the 3 phase is better than 5 phase, better than the previous phases. But keep in mind, in the 3 phase system, it is, I mean, it's cheaper in terms of the overhead cost. Now, as we know, in the 3 phase voltages and the currents, there is two sequences. There is a positive sequence and there is a negative. So the positive sequence, we used to call it ABC. So A with angle 0, B with angle negative 120 degrees, C with positive 120 degrees. The negative sequence, very similar, but we used to call it ACB. So this make it A with 0, B is C with negative 120 degrees, B with positive 120 degrees, which is good. Again, it's called positive and negative sequence. You just need to be familiar with those. Then the other thing that you need to be familiar, which is V line to line equals V line to neutral divided by square root of 3. This thing is very important and you need to make sure that you understand it. Or we can say V line to neutral equals V line to line times square root of 3. Then there is an angle. It can be positive 30 if you are positive sequence, or negative 30 if you are a negative sequence. So I encourage you to recall the 3 phase, make sure that to understand it very well. 3 phase standard assumptions, every time we are assuming picking up phase A as a reference. So with angle 0, all of the voltages given are line to line, not line to neutral. All of them are line to line, unless it's mentioned that this is not line to line, this is line to neutral. The other thing, every time assume a positive sequence, every time with ABC, and every time assume the positive, this is with 0, negative 120 degrees, this is with positive 120 degrees. That's what we will assume every time. All right. Now the Y connection, Y connection is based on 4 wires. So 4 wires, basically, most likely this is used in distribution. Why it's used in distribution? Because you have load 1 with home number 1, which is connected line to neutral. Load 2 with load number 2, line to neutral. Load number 3 with load 3, so line to neutral. This is Y connection. Delta is used a lot in transmission. In the transmission lines, basically in medium voltage and high voltage, you will see only 3 phase. You will see the medium, low voltage and medium voltage. It's based on a 3 phase system, and the other thing, 3 wires. I would say. I'm sorry. 3 wires for phase A, B, and C for the transmission, and there is earth, while there is no neutral. No, neutral wire. And neutral, this is even in transmission and sub-transmission. So no matter if you are in sub-transmission, there is no neutral wire. Keep this in mind. This is very important. Why there is no neutral? Because when you are transmitting the power from substation I to substation J, there is no intermediate load in the middle, and assume the system three-phase is balanced. Once it is balanced, this makes IA plus IB plus IC equals 0. Once all of them, they are equal to 0, which is the same as I neutral, this means the neutral current is 0. Then why do we need to put a fourth wire or a neutral wire while the current is 0? So it will be meaningless. However, in the distribution, no, we must put it. Otherwise, we cannot connect electricity. I mean, you cannot connect phase A alone with nothing. There is no returning path for the current. So we need to use it to complete the circuits, and to get the neutral, especially in the distribution. While in the transmission and sub-transmission, there is no neutral. How to calculate the delta currents? I mean, just like self-reading, you should be aware of how to use this before. Then delta Y transformation. Delta Y transformation, which is basically we would like to transform the impedance from being delta to be Y. How can we do this transmission? So we have ZA, ZB, ZC, and ZAB, ZCA, ZBC. So ZA, look, multiply the adjacent, divide by the overall. So Z of anything equals multiply adjacent divided by the sum of all. So look at ZA. Where are the adjacents? ZAB and ZCA. So ZA equals ZAB times ZCA divided by ZAB plus ZBC plus ZCA. Then how about if we need to calculate ZB? ZB, look at the adjacents, ZAB and ZBC. So it will be ZAB times ZBC divided by ZAB plus ZBC plus ZCA. How about the last one, ZC? Look at the adjacents, which is basically ZBC times ZCA divided by the sum, ZAB plus ZBC plus ZCA. Okay, which is 2 times the adjacent, multiply the adjacent and divide by the sum of all of the rest. Then how about the opposite, converting Y to delta? I mean, previous one was delta to Y. Now converting Y to delta. So you will realize that the adjacents, ZA and ZB, add them, then multiply them, divide by the last one. ZAB. So here, adjacent one plus adjacent 2 plus adjacent 1 times adjacent 2, divide the opposites. So when you look at it, to calculate, for example, ZAB, the adjacent ZA plus ZB plus ZAB, ZA times ZB, divided by the adjacents, or the opposites, which is we use ZC. Then the same thing for ZBC. ZBC equals ZB plus ZC plus ZB times ZC divided by ZA. Then the last one, ZCA, which will be ZC plus ZA plus ZC times ZA divided by ZB. Okay, that's the delta Y transformation that you need to be familiar how to do the transformation. Now, let me pause here. Let's stop here. Any question? Does anybody have a question? Okay, so I'm gonna stop the recording now. اوكي، حد عنده سؤال، شيء، اي استفسار قبل ما نخلص؟
No, thank you so much. I think it's all good.
All right.